We'll finish up, I think this is 5.7. No, not 5. 9.7, yeah. Here's a summary of electron configurations. The lower energy orbitals fill before the higher energy orbitals. Just like when you go to a hotel, generally the cheaper rooms fill up first, right? And what's left over, it's like the honeymoon suite that's like $500 a night. So the lower energy orbitals fill first. Orbitals can hold no more than 2 electrons each. A bed really should hold no more than 2 people, right? So orbitals are like the beds in the hotels. No more than 2 electrons. And when 2 electrons occupy the same orbital, they must have opposing spins. Okay, that's called the Pauli exclusion principle. When orbitals of identical energy are available, they're going to fill singly first, and then they'll pair up. So if you have a room where you're paying the same amount regardless of which bed you sleep in, people are going to take their own bed first before they sleep in a bed with somebody they don't know, right? That would be weird. Or when you're getting on the bus, if there's empty seats, you take an empty seat before you sit next to a stranger. So the electrons will take their own orbital before they pair up. They'll only pair up if they have to. So let's write some electron configurations. We're going to do electron configurations and orbital diagrams for nitrogen, oxygen, fluorine, and neon. What color do I have here? Let's do that color. So let's look at nitrogen first. And I think it's helpful when we're first starting to do the orbital diagram first and then the electron configuration. So the orbital diagram is going to have the little boxes, and the first orbital is the 1s, and next in energy is the 2s, and then comes the 2p, which is 3 orbitals, but they're all the same energy. Then after that would be 3s. But this is as far as we need to go. And then we're going to put the electrons in there. We need to, let's see, I'm choosing a color here. Not very decisive today. So we need to know how many electrons nitrogen has. So we look at the periodic table, it's got 7 electrons. So we're going to fill these up and count electrons as we go. So the first one will go in here, that's 1. And 2. That's the cheapest room. That's the lowest energy, and so they're going to pair up in there to save energy or to save money, depending on how you're thinking about it. And then the next one is the 2s, and again they're going to pair up in there. And so we've got 4 electrons. We need 3 more. So the next one's going to go up into the next highest orbital. But there's 3 of them, so that one will go in there. The next one is going to take his own seat on the bus. Okay, he's not going to pair up unless he has to. And then the third one here is going to take its own seat, its own orbital. So electrons would prefer to have an orbital all to themselves. Okay, and then they'll pair up if they have to. So that's nitrogen with 7 electrons. To write the electron configuration for that, we just look at our orbital diagram and write down what's in each orbital. Anybody else find that squeaky fan really annoying? And now it will be that I pointed it out to you. So this will be 1s2, 2s2, and then in the 2p orbital there are 3 electrons. So that's the electron configuration for nitrogen. If we look at the superscripts and add them up, 2 plus 2 plus 3 equals 7. 7 is the atomic number of nitrogen. This is kind of a check. If your superscripts don't add up to the right number, then obviously something was wrong. Any questions? Whoops. So let's look at Actually, I should have done it this way. So we're going to make nitrogen be green. And now we're going to do oxygen. We'll make oxygen orange. I don't know why. Oxygen's orange. Oxygen has one more electron than nitrogen. So the orbital diagram is going to be the same with one more electron. That electron is going to go into this orbital and pair up because there's no more empty orbitals at that energy level. In order to have its own orbital, it'll have to go to a higher energy situation, and it doesn't want to do that. Okay, so that's what oxygen does. And then the electron configuration for oxygen will be very similar, 1s2, 2s2, 2p4. So it's got one more. So let's do fluorine. Make fluorine yellow. Well, fluorine's got one more electron than oxygen, and so that extra electron is going to have to pair up. And then when we write the electron configuration, it's 1s2, 2s2, 2p5. 2 plus 2 is 4 plus 5 is 9. Fluorine has 9 electrons. So we're just kind of keeping track of what orbitals are these electrons in. That's all an electron configuration does. And then what about neon? So here's neon. Neon will be pretty pink. Well, neon's got one more electron, and so that's going to fill in there. Isn't that colorful? I like crayons. This is grown-up crayons, right? So then what's the electron configuration? It's 1s2, 2s2, 2p6. As one of my kids said, this is not rocket surgery. Okay? It's weird. Yes. It's strange and different, but it's really not that complicated. It's like learning a new board game where they can read you the rules and you're like, that didn't make much sense, and then you start playing it and you make corrections, and after a while you're like, oh, okay, I see how it goes, and then you remember it. A lot of chemistry is like that. I'm explaining it to you and it doesn't make a lot of sense, and then you practice, and that's the nice thing about that online homework is you get immediate feedback. Yes, I did that right, or no, I did it wrong, let's try again. And so that's like playing a game with friends who know how to play it, and they say, no, you can't do that. You can't play that card now. You have to wait for your next turn, right? If you can learn how to play board games, you can learn how to do this. Okay, it's just not that, it's weird, but it's not hard. So what do you notice about this electron configuration for neon? All those boxes are full, aren't they? The next orbital would be in the next shell, up into 3. And so for neon, all of these are full. That's a particularly stable electron configuration when the highest energy level is full. So the electron configuration of neon represents the complete filling of the n equals 2 principal shell. And we'll find out that that's important. We do have a shorthand that we can use. It's called a noble gas shorthand or noble gas configuration. And what we do is we say, well, let's look at sodium on the periodic table. Sodium has one more electron than neon. So instead of writing the whole electron configuration, we'll just write neon in brackets and then write the rest of it. So let's look at that. So the electron configuration for neon we just did. Neon is 1s2, 2s2, 2p6. So if sodium has one more electron, then it would have 1s2, 2s2, 2p6, 3s1. So this is the same as neon. And so to abbreviate that, we can just write the symbol for neon in brackets and then write anything that comes after that. So both of these are valid electron configurations for sodium. Yes?
So now you can do that with
Any of them.
After neon?
Yeah, I mean, you can use helium, but it doesn't really save you much. So, you know, for like nitrogen and carbon and stuff, we wouldn't usually put helium in there. But when you get to some of the bigger ones like cesium, and you use xenon, and then just add one electron, that saves you a lot of writing. So you should be able to write the electron configuration either way, and be able to recognize them either way. If you're given an electron configuration and asked what element it is, one of the ways you can identify that is by adding up the electrons. So we look at this full electron configuration. 2 plus 2 is 4, plus 6 is 10, plus 1 is 11. You find element number 11 on the periodic table, it's sodium. If you were given this one, you could look up neon. Neon has 10 electrons, and this one has one more, 11 electrons, and so it's sodium, number 11. So let's write electron configurations for these elements, aluminum, bromine, and strontium. So aluminum is element number 13. And so we're going to just start out and fill these up and keep track of how many we've got. So 1s2, 2s2, 2p6, 3s2. So we've got 12, and we need 13 electrons, so the next one's going to go 3p1. What would be the noble gas shorthand for that? Well, you find aluminum on the periodic table, and you go up a row and over to the end to find that neon is the noble gas that comes before aluminum. So 3s2, 3p1. Those are the two variations of electron configurations for aluminum. In the next section, we're going to show you how you can just pull this off the periodic table. But we're making you do it the hard way first. How about bromine? Bromine's got 35 electrons. Bromine's a big guy. Let's just do the noble gas shorthand for him. What's the noble gas that's before bromine? It's argon, right? So we can put argon in here. And argon is going to have an electron configuration that ends in 3p6. And so what does bromine have after that? What comes after 3p? It's 4s. 4s can hold 2, and this is where things get wonky. You know, they're all kind of staggered. Next is the 3d, and that one's going to be full. And then the 4p, and that's going to have 5. So where am I getting these things from, right? We had that order of filling earlier in the section. And so you go through that order of filling. S's can hold 2 electrons, P's can hold 6, D's can hold 10. Okay, and so you're going to fill them up until you get to the end when you have, you know, I didn't need 6 there because that would have been krypton. I only needed 5 electrons. Any questions? There's got to be questions. No questions. How about strontium? Well, strontium's just a little past bromine, isn't it? It's in the next period, it's in the next row. And bromine is right before krypton. So strontium, we could do krypton plus, so krypton would be end in 4p6. And so the next level is 5s. And strontium would have 2 electrons in there. So krypton has 36 electrons, plus those 2 in the 5s gives us 38, which is strontium. I'm going to write this whole one out as well. 1s, 2, 2s, 2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. If you add all those superscripts up, they should add up to 38. Now that order is a little hard to remember, right? Because it gets all staggered. You can draw the little chart that we had, but that's kind of tedious too. So we're going to show you how all of this information is hidden in the periodic table. But I guess first we need to do an orbital diagram for argon. Orbital diagram, that's the boxes. So we're going to do argon, and let's just draw our boxes. 1s is first, and then 2s, and then 2p, and after 2p comes 3s and 3p. Up to that point, they go nicely in order. So argon has 18 electrons, and so then I'm going to fill them in. 1, 2, 3, 4, 5, 6, 7. They're going to fill separately first. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Argon is a noble gas. It fills those boxes up completely. The next level with the 4s is empty. Any questions? Orbital diagrams are real helpful when you're learning to do this, but we don't actually use them a lot. They're more of a learning tool.